So let's start. While these people are still working extremely hard to get you power, we also will get a ventilation unit, hopefully, at some point. And so today, traditionally with the COSIC course, we also have one day which is focused on hardware security. And there we try to give an overview of what we do on the hardware side. So I start a bit with a general high-level decision, what I consider hardware design or hardware security, and how secure hardware design is different from other hardware design. Maybe how to address the complexity, a bit of the hot topics, and actually that's what we want to show you today on the agenda. The problem is often when you talk to people, what is hardware design? If you talk to an OS designer, then that person will say, okay, hardware design for me is actually the architecture, the microarchitecture of the processor. Often hardware is just one level what's below what you're working on, right? For a network system designer, for him or her, the hardware design means I assume there is a router box that I can work with. If you talk at COSIC to all the cryptography people, for them hardware design is us, the hardware group that works on VHDL, Verilog, maybe puts it on an FPGA, on an ASIC, right? For someone who works on IoT devices, like you had the presentation of Leonard yesterday, it often means I want my design to be attack resistant against side channels, against faults, against any other type of manipulations. And often also for the digital designer, what is hardware design is often the standard cells, the technology. You might have heard about Trojan circuits during the processing cycle of ASICs and so on. So how do we get a bit of order in this complexity? For that, I go back to some old definitions on trust and trust boundaries. And I go back to a definition of Ross Anderson in a very readable book, which is called Security Engineering. And he has his definition after the NSA. And he says, a trusted system or component is one whose failure can break the security policy. A trustworthy system or component is one that won't fail. So there is somewhere a root of trust or something you trust, and if that breaks, the whole thing can fall apart. The Trusted Computing Group also had at some point a definition, and it says an entity can be trusted if it always behaves in the expected manner for the intended purpose. Loosely stated, if trusted systems or components fail, bad things will happen. And so the goal of the security is to minimize what needs to be trusted. What is it that we need to be trusted, and can we build something on top of that? So that's why we're trying to search what's the root of trust. And we can go back to our list of topics. For the network system, it says, I have to trust the router box. For a secure boot, these people say, we have to trust the TPM, we have to trust the secure element, depending what you're working for. Same for this OS designer. He or she will say, I need to trust this architecture, microarchitecture of a processor, and so on, right? Cryptographer has to trust this one. They have to act for IoT devices and others. We have to add attack resistance, side channel attacks, faults, manipulations, and so on. And I can continue like that, right? So that's why actually we came up long time ago already what we say, what is a design method? This is how a design method to approach this complex problem of secure design. And so we decompose. For instance, we start at the application level, and we say we want a secure communication between, I don't know, a tower and a cell phone or a SIM card or something. And there at that level, you define the security properties you want, like confidentiality, integrity, identification, things like that. But that relies on maybe some quality cryptography, public key, secret key. These days we focus a lot on post-quantum cryptography. The cryptography has to run on the architecture, hardware, software type of platform. You see processors which provide TEEs like SGX. We've done some exercises here which we call Sancus. That relies on the microarchitecture. We see some of that, like crypto co-processors, instruction sets, and so on. We decide on logic circuits, maybe secure memory. And even at the bottom, we have random numbers and physically unclonable functions. Because many of the crypto protocol designers, they assume there is some freshness, there is some entropy, there is a random. We assume Alice and Bob exchange random numbers, but designing a true quality, true random number generator in hardware, it's extremely tough thing to do. We might have to rely on technology at the bottom. So the way we look at this is that the root of trust for us is a component at a lower abstraction layer upon which the system relies for its security. So, and that's what we try to do a bit by selecting a set of hot topics. What we try to do a bit today is identify some of these layers and the hot topics that people are working on these days. And so yesterday, you also had already a very nice introduction and on hacking, hacking for starters by Leonard. And so it's not only that you have to think about all your layers of abstraction, it's also you have to think about your circuit or your component or your design from concept to retirement. That you design it, you manufacture it, you deploy it, you have to maintain it, and often what's forgotten, you have to dispose of it carefully, because we extract circuits, we extract secrets from things that people have thrown away. Since we are doing hardware, I also want to link this to these days, both the EU and the US have developed what's called CHIPS and Science Acts. I have here a copy of a document from the US CHIPS and Science Act, because it's very readable. It's a very short document, 25 pages, and it has a whole section on what we should do at security and chip design. We're not going to read this whole thing. I'm just going to point out to a few topics. It says semiconductors and system security. It says every aspect of the system must be considered. That's exactly what we do. We do that by introducing all these layers of abstraction. It must be robust against side channel attacks. So in a document of 25 pages, the US president talks about side channel attacks. So you see the importance of this topic, right? Security must be pursued as an integral part of design, not as an add-on after the chip is designed. That's too late. Because we often see protocols which are not secure or solutions which are not secure, and then they say, okay, can you fix it? That's way more expensive than thinking about it during design. They encourage open source, but they realize it's not easy in the context of semiconductor design, semiconductor companies. And then at the bottom, there is a list of topics we should be working on. It's 6 topics. We're also not going to read all of them, but I'll point some of them, right? So one of them is the security, secure hardware with implementation of post-quantum cryptography, implementation of low-power cryptography, other privacy-preserving hardware implementations for processing encrypted data. This falls under the category computing unencrypted data, and we had an introduction on that yesterday on the topics of fully homomorphic encryption, multi-party computations, and so on, right? And topic 1, secure against various forms of attacks on operations. So I'm only allowed to have here a few introductions, a few minutes of introduction, but that's what we're going to do today. We're going to select a few of these layers of abstractions and see what is a bit the state of the art at this moment. And we actually start at the bottom, and we actually have a first presentation by Miloš. He's an expert on how to do true random number design. So where do you get your entropy? Then we have a presentation on physical side channel attacks, so that's a bit one level up. Then we have a bit of attacks on the interface between architecture and microarchitecture by Jo van Bulk. And this afternoon, we actually focus on what are the newest crypto algorithms which need acceleration, which need implementation in hardware. We have one by Wouter on FHE acceleration, from hardware to compiler. We have one on FHE applications, what we can do with it these days. And to finish, at the end of the day, Suparna will talk about post-quantum cryptography. We had already a couple of presentations this week on post-quantum cryptography, but these have now a new set of implementation challenges, and that's what we will do at the end of the day. And that is my short introduction to the day. So if there are any questions, please let me know.